Phobos is a small, elliptical, and highly irregular moon orbiting Mars. The shape was derived from Viking orbiter Phobos. Interpretation of surface features like craters and grooves on Phobos and other small bodies in the solar system requires an understanding of the balance between the forces which move objects. Over the next few tens of millions of years, Phobos will approach Mars, resulting in lower, faster orbits and a larger gravitational effect of Mars on Phobos. Phobos is unwrapped so that the entire surface can be seen at once. The same side of Phobos always faces Mars, the direction of which is indicated by the arrow. Gravitational forces are represented as needles around the surface of Phobos. The magnitude of the force is represented as a height field and summarized as a histogram. A quantity called effective topography shows which way an object would roll on the surface. With this color map, objects would roll from yellow to red to blue areas. Total gravitational force is the sum of effects from the isolated mass of Phobos and tidal gravitational forces of Mars. The distance 1.0 represents the current orbital radius. The simulation of combined effects covers the distance from 1.8 times the current radius, where tidal forces are negligible, to 0.75, where tidal forces are comparable to Phobos' own gravity. To illustrate how the forces add, we will first look at Phobos in isolation, ignoring tidal forces. Since Mars is ignored, the effective topography is unchanging as Phobos approaches Mars. The effective topography color map is equivalent to the real topography, indicating that an object on the surface would move towards the bottom of the crater. Now only the tidal effect of Mars is shown. As Phobos approaches Mars, the tidal forces become large and point away from Phobos at the points nearest and farthest from Mars. Gravity and tidal forces are added together to show the effective topography as Phobos approaches Mars. As distance decreases, down becomes the ends of the moon nearest and farthest from Mars. In particular, at the large crater near the arrow, a ball would roll from the left rim down to the bottom, then up the right rim. We dramatize the gravitational effects by mapping the effective topography to radius so that virtual downhill is represented as dips in the surface.